Good afternoon, and thank you for attending the Steel Joist Institute's webinar, Steel Joists for Any Application, Specialty Profiles. My name is Stephanie, and I will be moderating today's webinar. Today's presenters are Ben Pitchford with New Millennium and Doug Hoffman with Volcraft.
My name is Ben Pitchford. I'm Engineering Manager at New Millennium Building Systems in Lake City, Florida. It's a pleasure to be with you guys today. We put this webinar together to talk about a few different things. First, we're going to start with some standards for SGI shapes. Next, we're going to look at some slope seats, some slides regarding slope seats, and work our way into pitched top chords, probably the most common application of special profile joist. And then we're going to continue on. Doug's going to talk to you guys about joist and a hip roof, and eventually we're going to just talk about some general special profile joist, some things beyond just pitched top chords. So the big question is, we're talking about specialty shapes, specialty profiles. What makes them special? Well, the answer may seem very obvious, but it's not a standard shape. So in order for us to talk about what's special, we need to take some time to talk about what is standard. So standard SGI shapes. Going back many decades, we have now the K-series joist, which is 10 inches all the way up to 30 inches deep and up to 60 feet long. Then you work your way into the current LH series joist right now, 18 inches to 48 inches deep, up to 96 feet long. And then we have deep long spans, BLH. Those range from 52 inches deep all the way up to 120 inches deep, 10 feet deep, and up to 240 feet long. And then don't forget, we also have joist girder, the primary members that are typically supporting steel joist. And those can vary 20 inches, similar to DLH, all the way up to 120 inches deep and up to 120 feet long. So out of all these, most common is for the top chord and the bottom chord to be parallel. You can see a generic picture on your screen. You see the truss system, the web members between the chords, and you see the two chords, top and bottom, parallel to each other. This is most often used in floors and flat roofs, maybe low slope roof. But yeah, this is the most common. This is the bread and butter. This is what the majority of the joist that joist manufacturers are building are going to look like. All that changes is really the depth between the chords and then the length as far as the length of the chord. So if most common is parallel chord, what are some other options? Well, joists are also used in sloped roofs where you would have a high support and a low support. And those support elevations can change, and obviously the greater the difference in elevation, the greater the slope of the joist. So when you have conditions like that, we just want to take a few slides here and talk about the slope seats that go on those joists. So where steel joists or joist girders are sloping, the end bearing or seats, they also may need to be sloped. However, it's important to note for K-series joist, the seats are permitted to not be beveled for slopes of 1/4 inch or less per foot. So let me say that again. For K-series joist, the seats are permitted to not be beveled, not be sloped for 1/4 inch or less per foot. And we're going to talk about why that is. So you can see a picture here that's actually a joist that is actually sloping 1/4 on 12. You can see a slight difference in elevation at either end of the joist. And in this case, this is a scenario where the joist manufacturer, per the Steel Joist Institute, would typically not slope the seat. So you may be wondering, why is that? What's going on here? So what actually happens is you do end up with a small gap where the joist is bearing. On your screen, you can see that's a joist sitting on a beam. It could be sitting on a wall or some other structural member, a joist girder. And what happens here is that there is just a small gap, and the erector in the field is able to weld through that gap. There are limits for AWS, but at a 1/4 on 12 slope, you don't end up with a gap large enough that the erector would not be able to weld through that gap. So let me show you an example of a gap that cannot be welded through. So you can clearly see right here that that is a pretty large gap. This was a scenario that ended up requiring either rework of the seats to the correct slope, or you would have to use some kind of shim plates in here. But you can see, as the slope increases, this problem increases if you don't fabricate the seat at the correct slope. So continuing on with slope seats, when slope seats are required, the seat depths, they need to be adjusted in height specifically to allow for enough clear bearing for our end webs. And what the SJI does to address this is they require two tables. They specifically have table 2.2-2 and -3. We're going to look at the titles of those tables here. So first is table 2-2, which is slope seat requirements for K-series open web steel joist. And you can see here that the table is labeled for slopes 3/8 on 12 and greater. And that's because we've already addressed and discussed the fact that the 1/4 on 12 joists don't need to have slope seats. So this is for 3/8 on 12 and greater. And then the next table is 2-3, and this is slope requirements seat depth for LH and DLH series joist, again for 3/8 on 12 and greater, LH and DLH series joist. So let's look at a better image of what these tables are actually talking about. So most common is a parallel chord joist. We discussed that earlier, and sometimes those joists have different bearing elevations and the joist has to be sloped. Specifically, the SJI Code of Standard Practice has requirements for the seat depth, and it really becomes a concern at the high end of the joist. You can see in this table here, this is talking about LH and DLH joist, 3/8 and 12. You can see on the right side here, these charts here say CD, C the letter D, and over here you can see that as my slope increases, my seat depth required at the high end also increases. We'll talk a little bit more about what's going on there. Basically, what happens if we don't have that required seat depth, our end web coming up into the top chord does not have enough clear bearing, as we say, to get over the bearing and have a good reaction on the structure, whether that's a wall or a steel. So very important to pay attention to seat depth at high end. So moving on, let's actually get into some specialty profiles here. First is pitched chords. Pretty simple. We use the word pitch kind of like a pitched roof. The next thing we're going to look at later when Doug takes over is arched, or sometimes people say curved chords. So there's 4 standard types of SJI joist with pitched top chords. First is a double pitch, and you can see here a double pitch pitched 2 ways underslung. You can also do a double pitch that has square ends. The next 2 are both single pitch. The first is top chord underslung. And then again, you can do single pitch joist with square ends. Now you notice here on the double pitch side that this ridge on this joist is in the very center of the joist. There are examples that will follow later for actually putting the ridge at a different location on the joist. It's also important to note that these snips here taken from the SJI catalogs, they're generic. The web systems are going to vary by manufacturer. So if you have specific requirements, for instance, maybe this is a gymnasium and you have ductwork that needs to pass through here and you want a certain size duct, definitely need to get with your local preferred joist manufacturer and discuss with them what options we have as far as fitting that through there. I've also seen very large joists where they even have catwalks that are framed through the opening in a joist. So certainly some options there to consider, but make sure you're not just assuming what the joist manufacturer, how they will build their joist and where web members will be located. Make sure to have those discussions, and as early on as the project as possible would be helpful. So next, we're going to look at specifying a joist that has a double pitch top chord. So what depth is used to specify the joist? I know this is a big question that I've discussed many times with many people specifying joist, and it's important to note that there is a correct answer. So when specifying double pitch joist, the designation depth is the depth at the ridge of the joist. So you can see the arrows there. The designation depth needs to be at the ridge. So here's an example I mentioned earlier. We're going to look at something that's actually offset. So you can see here that the ridge location is actually not at the very center of the joist. It's actually closer to the right end of the joist. In this case, that's fine. Certainly allowed to do that, and there's times in a building where this would make sense and would meet the needs of the project. In this case, you still designate the depth of the joist using the ridge location depth, not the depth at the midspan of the joist. And it is a common misinterpretation to also give the designation depth at the ends of the joist. We want to give the designation depth at the ridge location on a double pitch joist. So next, let's look at single pitch joist, the second to SGI standard joist. So specifying a joist with a single pitch top chord. Again, let's ask ourselves the same question. What is the joist depth? You can see the picture here, single pitch joist, the top underslung, bottom square end. So single pitch joist, the designation depth is always at the midspan. Obviously, we cannot use the word ridge when it applies to a single pitch truly, because there's no change in pitch or slope. It's sloping, it's monoslope. It's going one way the whole time. So what we define here, SGI says single pitch joist designation depth is at the midspan of the joist. So here, let's look at a more specific picture. You can see the different bearing elevations, the sloping top chord, the pitch top chord, and you can see that we're going to pull our designation depth at the span divided by 2, so exactly at the midspan. So it is critical that structural drawings provide all necessary dimensions and joist depth. You know, if no special layouts are requested, the joist manufacturer is going to choose the most economical web layout based on the joist geometry and the loading. So if there's special requirements for web layouts, they must be specified. So this goes back to what I mentioned earlier. If you have ductwork, maybe something large like a catwalk that you want to pass through the web system of the joist, those things need to be given and outlined early in the project and definitely on the structural drawings. This is going to give the joist manufacturer the information they need to make sure they both quote and design and build the joist correctly to meet your needs in the field. So a specific note we need to discuss about SGI designations. You can see an example. This is a snip out of the K-Series table, ASD design. In a quote from the Steel Joist Institute, the load table applies to joist with either parallel chords or pitch top chords. Joist can have a top chord pitch up to 1/2 inch per foot. However, if the pitch exceeds this limit, the load table does not apply. So I'm not going to read all that to you again, but I want you to hear it, that these load tables are intended for joists that are parallel chord or 1/2 inch on 12 slope. If it's greater than 1/2 inch on 12, these load tables do not apply. This is both for K-Series and LH and DLH series. So let's go through an actual design example that helps us, put this all together, some of the things we've been talking about. So let's take an example of a 100-foot span, and let's say the joists are going to be spaced 10 feet on center. And that's something we'll talk about a little bit later, but certainly with special profile, larger joist, you want to consider this joist is very special, is maybe very large, very heavy. It may not be most economical to build all of these special joists and then space them on 4 or 5 feet centers. Want to look at, can we do something like 10 foot on center and then address the product I'm putting over the top? If you're doing steel deck, you could just look at a deeper steel deck. You could look at a 3-inch and roof deck. And like I said, Doug will talk about that a little bit more later too. So here's our example, 100-foot span, 10-foot spacing. We want the top chord sloped at a 1/2 on 12. We want the bottom chord flat just for architectural reasons. We know that we've already calculated we want end depths of 31 inch and 81 inch. We want a mid-span depth of 56 inches. We also know the total load requirement for the project structurally is 40 pounds per square foot. Now notice this here, since this is going to be a single pitch joist, the designation depth is going to be 56 inches. We already know that that's the mid-span depth, so we know that that's what we're going to use to designate our joist. So continuing in the example, you know, we already said this, we're going to use a single pitch because of the size of the joist. We know we're outside of the K series tables and LH series tables, so we're into the DLH series tables, and we're gonna use the tables to pick an appropriate DLH series joist, even though it's going to be single pitch, because we know it's half on 12, so it's within the limits of the Steel Joist Institute. So continuing again in the example, we know we have 40 pound per square foot requirement total load at 10-foot spacing. Simple math we can all do. We need 400 pounds per linear foot total load capacity. So once we know that, we want to start entering into the SJI load tables to figure out what joist is going to meet our needs. Here's a snippet we took from the 56 DLH series joist. You can see designations between 11 and 16. You can see here 11 up to 16. You can see the load capacities increase. So we know that the span of the joist is 100 feet. We know we want 56-inch deep joists. So the last question is, I need a capacity of 400 PLF. So if we come down in the table, we're going to find that a 56 DLH 14 is what I need to designate. A DLH 13 isn't quite there. The black number, the total load, is only 386. So we're going to pick a 14, gives us a little more capacity than we need, but it meets our 400 PLF requirement. So we know we've chosen a 56 DLH 14. So let's continue here. Now we want to look at seat depths. Since the top chord is sloped half on 12, we referenced this earlier from the Code of Standard Practice regarding seat depth. At the low end, not really a concern. You can see here that bringing that end web in at a low end is not an issue. So we certainly could just designate standard 5-inch deep seats right there, 5-inch minimum. However, if we continue and looking at the high end of the joist, this is where we're going to have the concern we talked about earlier, where we mentioned that variable D. So here you can see that picture we looked at earlier. And if we reference the chart, we're going to find here on the left that when my slope is half on 12, and in this case we know that's the pitch of the top chord. So effectively what the SJI table tells us is that we need to at least have a 6-inch seat depth at the high end of the joist, 6-inch seat depth. So when we designate this joist, we need a 6-inch deep seat at the high end of the joist. So now we do have to think about something else. There is something to be said for consistency in the design and building of the steel joist. So what we would recommend here, since the low end is 5-inch minimum, the high end 6-inch, go ahead and specify 6-inch seat depth at both ends just for consistency. Then there's very clear, you don't have to talk about two different depths. You can just say 6 inches deep seats at both ends. So in summary, looking at our single pitch design example, we chose a 56 DLH 14 from the load tables. It's going to span 100 feet. It's going to be spaced 10 feet on center. It's an underslung. Top chord slope is half on 12. So you can see the picture here, basically from earlier. We noted the midspan is 56 inches deep. We know the shallow end is 31 inches deep. We know the deep end is 81 inches deep. And what we finally discussed there, the seat depth, 6-inch deep seats at both ends. So as we said earlier, we've gone through all this work. We're designing the building. We know our depths. We know what designation we want. Make sure all of this information, if you're actually creating the structural drawings, make sure this information is actually on the drawings. We don't want to leave any question marks for the steel joist manufacturer as far as Maybe you gave us the midspan depth and the shallow end depth, but you didn't tell us the deep end, and you didn't tell us the pitch of the top chord. Or maybe you tell us the pitch of the top chord and you don't tell us what the depths are. We need all the pieces to the puzzle so we can make sure that we build the correct joist. And certainly it helps to have that information on the drawing and not have to follow up with questions later as far as what we want. So I know some of you are thinking, I do buildings all the time, designing buildings. I see buildings where the pitch of the roof is greater than half on 12. So what do we do? What do we do if the top chord slope is greater than half on 12? So instead of going to the load tables for DLH, LH, and K-series joist, we want to use a load over load designation. Many of you have maybe heard that, maybe you haven't. Basically, we're going to define the actual load requirements of the joist. We're going to give the total load, the dead plus live generally, slash the second number is the live load. And you actually can see there actually are even some load over load tables given by the Steel Joist Institute in this LH series table here. You can see at the top. This gives you some information if you are going to design load over load joists and you want to know, for instance, approximately what is the self weight, what's the weight per foot of that joist, what's the approximate IX of that joist. Some information in the SGI tables can help you with your design there. I also want to point out, when you get into larger pitched joists that are greater than half on 12, often you're going to hear the term gable joist. Generally, that just means it's a deeper joist with a steeper pitch. So double pitch generally is a lesser pitch. If you start throwing around the word gable, generally we're just talking about bigger joist with greater pitch on the chord. So what if the top chord slope is greater than half on 12? Again, you may also label the joist as SP, special joist, and provide a load diagram. So here's an example. No specific numbers are in there, but just an example of what can be given. So if there's more than just total load over live load going on, there's axial loads, end moments, snowdrift loads, concentrated loads from mechanical units, something hanging on the bottom chord. You can give all that information in a joist load diagram. And also in that same diagram, that would be a great place to give the pitch information. You can say, this is my depth at the ridge. This is my depth at the left end. This is the pitch of the top chord. And all that information will lead to us being able to quote and design and send to the job site an accurate joist that meets the needs of the project. And this is also great if you just have complex loading. Again, like I said, if you have more than just dead and live load, this is a great way of doing it. So let's do another design example, but this time we're going to go a little bit outside the tables and we're going to look at a 60-foot span. And this is going to be a top chord sloped at 3 on 12, but rather than single pitch, we're going to look at a double pitch. We're also going to look at bottom chord bearing. So this is a little different than our example before. So we're over the half on 12 limit of the SGI tables. We're also double pitch, and we want square ends. We want this thing to be bottom chord bearing. And you can see right there, that essentially means that my support, whether it's a beam or a wall, is going to be right underneath the end of that end vertical right there. It's going to sit on its bottom chord rather than on a seat at the top chord. So again, design example, let's say a depth at the ridge needs to be 102 inches. That's already been coordinated. That's what the architect needs. Well, we know based on what we discussed earlier, that is going to be the designation depth. We know the designation depth, 102 inches. These joists are going to be spaced 6 feet on center. We know the live load requirements of 20 pounds per square foot and dead load 20 pounds per square foot. So based on what we know of a total load over live load designation, the example we did earlier, we're going to add our live and dead together, 40 PSF times our joist spacing, 6 feet on center. So we know total load is going to be 240 PLF. That's our first number right here. Second number is just live load. So 20 PSF times 6 feet on center, it's going to give us 120 PLF. So 102 DLH, 240 PLF over 120 PLF is our designation. And we also know based on the 3 on 12 and based on 102 inch designation depth, we can calculate that the ends depths are going to be 12 inches deep. So to put this as a real example, here's actually a pretty close example of what we were just looking at. This is actual gymnasium with actual double pitch joist over the top. You can kind of see the bottom chord here. You can see over here that you're bearing on the bottom chord. You can see it's very deep at the ridge. It's sloping down. I know it's kind of hard to visualize one single joist because there's so many going on there. It looks like an optical illusion. So let's kind of highlight one of the joists here. And now once we bring that out and highlight it yellow, you can really see kind of what one of those joists looks like over that building right there. So let's talk about bridging. So specifically, whether you're using a standard SGI designation or you're using a load over load designation, the number of bridging rows needed is often greater for a special joist, special profile joist, than it is for a standard parallel chord joist. So again, if you have a special profile joist, double pitch joist, generally speaking, the bridging requirements are going to be greater. The number of rows needed is going to be greater for that double pitch joist than it is for the parallel chord joist. And we're going to talk about some more specifics of why that is. So first, one of the things that often happens is the center of gravity of a special profile joist often ends up being much higher. And in many cases, even on an underslung joist, the center of gravity of the joist itself can be over the bearing. So what you can imagine is that's a joist that if you set it up in the air and let go of it, naturally that joist is going to have a tendency to want to fall over, to rack over. In this case, what we say is we need to put some bolted erection bridging to stabilize this joist during erection. Basically, you're going to tie this joist to the next joist, and then they both work together with bolted bridging that's put in during erection to give stability to those joists. And as you continue down the line, the more joists tied together, the better. So continuing talking about bridging, based on the overall profile, it may be that all rows even need to be bolted erection bridging. So often special profile joists are very deep. Many times they're very long. And just one of the things you want to consider is, due to the special nature of them, just making all the rows of bridging bolted erection bridging. Something else I'll point out is that does not necessarily have to be designated by the structural engineer record on the structural drawings. Joist manufacturers are familiar with their product. They're familiar with using diagonal bolted bridging, erection bridging on special profile joists. So if you put a note, bridging per the Steel Joist Institute, per the joist manufacturer, that's going to give us what we need to know that we can take it from there and apply bridging to our joist as needed. So another point to make about bridging, the method of terminating bridging should also receive special attention, and it certainly requires clear communication. In many cases, the best approach to terminate bridging is to just use the last two joists. What this can do is allow you to put diagonal bridging in the last joist space. You may not even have to attach to the main structure at all. Often with these larger joists, deeper joists, may not have the structure designed to even take those bridging forces, so we can terminate in the last joist space using diagonal bridging. So continuing on again with bridging, when the joist space is less than 0.7, 70% of the joist depth, SJI also says bolted horizontal bridging shall be used in addition to diagonal bridging. So basically what we're saying is, when you have a really steep X, and I'm not drawing it well with a laser pointer, but if you imagine your joist is really close together, but it's really deep, and you go to put in that X, the X is really steep. It's not providing the same level of stability as a joist that was spread further apart and your X's become more horizontal. So what we do here is we throw in some horizontal bridging. So you end up with some diagonal and horizontal bridging at the same location. And those pieces working together give the stability that we need for the joist. You can see here the Steel Joist Institute's even made a table for this. They give some joist depths and increments here. And they say minimum joist space for only diagonal only bridging. And then if you're less than that, then you need to be adding horizontal bridging in addition to your diagonal bridging. So another bridging slide here is when we're looking at some of these special profile joists. We've talked a lot about underslung joist, but there's also bottom chord bearing joist. Our last double pitch example there was bottom chord bearing joist. You can see here that naturally when this joist is set, there's nothing, none of the center of gravity can possibly be below the bearing. So naturally this joist is unstable. It has a tendency to want to tip over. One of the ways we overcome that is we require that a row of diagonal bolted bridging, X bridging is required near the support. And near the support, you can see in the picture there, not necessarily directly over the support, but at least near the support, because this is where the joist is bearing, and it's all of that weight is over the bearing point. So we want to have additional row of X bridging required near the support. And again, whenever joists are bottom chord bearing, this is quoted from the SJI, diagonal cross bridging must be installed from joist to joist at or near the bearing location to provide additional lateral erection stability. So some rules of thumb we want to talk about when you're designating these joists. For square ends or bottom chord bearing joists, you can use those terms pretty interchangeably. We really want the minimum joist end depth to be 12 inches. And if we show this in a picture, here is a double pitch joist. It's bottom chord bearing on both ends. Graphically, what we're showing you is we want 12 inches minimum at the end there. And one of the main reasons for that is you can imagine, we don't show it here, but you have a top chord coming in, you have a bottom chord coming in, you have a web at the end coming in, your primary tension member, you have a vertical at the end that's carrying your reaction. All of that stuff coming together, if you get under 12 inches, it just gets really tight and really hard to fit everything together, especially on a very large joist where your chord sizes may be growing even into the 5, 6, and 8-inch range. It just becomes complicated. So a good rule of thumb, try to keep that end depth at least 12 inches minimum. So for underslung joists, we have a similar requirement. The minimum bearing elevation to the bottom chord should be 12 inches. So that is the minimum joist end depth should be the seat depth plus 12 inches. The minimum joist end depth should be the seat depth plus 12 inches. So again, let's use a picture. For an underslung joist, here's similar to before, but you can see the bottom chord drops down below the bearing elevation, double pitch top chord. The concern we have here is that from the bottom chord to the bearing elevation, we want that dimension to be at least 12 inches minimum. 12 inches minimum, you can see there. So you can, let me go back for 1 second. You can see the other requirement for 12 inches plus the seat depth is your end depth. So the end depth of the joist is your seat depth right here, plus 12 inches is the minimum depth at the end of your joist. All right, so for special profile joist here, here's another example of a very large double pitch joist. And notice that you can even actually take a bottom chord bearing joist, you can see over here, and actually extend the bottom chord out and create a cantilever. Similar to what you would often do with a top chord extension if it was an underslung joist. On a bottom chord bearing joist, you can continue this out and actually create a cantilever condition. A very large joist. So another note about SGI designations, we kind of want to circle back here because this is an important note. So we discussed earlier that the limit is a 1/2 on 12 for SGI series joists. So it is actually possible to exceed the minimum joist depths that we just talked about. For example, an 18 LH joist spanning 36 feet, and it has a double pitch chord of 1/2 on 12. If you do the math on that, you would end up with an end depth of only 9 inches. And if that was an underslung joist, there would also be a 5-inch deep seat on the end of that 18 LH. The bottom chord would just be only 4 inches below the bearing. Not going to tell you that's not possible or that's wrong. Just want to keep an eye out for that. And also be reminded that this information for half on 12, this note applies to all SJI series joists, K series, LH series, DLH series. Half on 12 is the limit if you're going to pull a designation from the table. Again, if you're greater than half on 12, that's okay. You just need to use a total load over live load designation, or go ahead and give us a specific load diagram with all the requirements that you have right on there. So another note about SJI designations, specifically KCS joists, constant shear joists. They have a constant shear and moment envelope. You can see an example here taken from the SJI catalog. KCS joists are a great tool to be used to specify, especially when you have non-uniform loads or you want future capacity. You're not sure what's going to be put up there right now, but you know something is going to be put up there later, probably a mechanical unit. However, the largest KCS joists already utilize angle sizes for chords that are compatible with 2.5-inch deep seats. So if one of these designations is used in a double pitch joist, the top chord has to increase to maintain the constant moment capacity due to the decreased depth. For instance, 30 KCS5, the largest joist we have, let's say it has a chord size of 2.5, which matches the seat depth. If I now make this joist a double pitch joist and my end depth goes shallower than 30 inches, in order to keep the same moment capacity, I'm likely going to have to design that joist with a larger chord. This now may become an issue. I may have a 3-inch chord, a 2.5-inch deep seat. Definitely something to be considered, because in this case, we really would need a deeper seat. We need a deeper seat in that case. So something to consider, just another item to be coordinated as you're working on your projects. And certainly contact your local joist manufacturer with these specific questions on a specific job, and we'd be happy to discuss it further with you. So what about maximum joist depth? Maximum joist depth. We talked about minimum, we talked about end depths, we talked about minimum slopes. So standard SJI designations, they range all the way up to 120 inches deep, 10 feet deep. Many SJI, maybe even most SJI manufacturers, they can even go beyond 120 inches. However, there are limits that depend on a number of factors. For instance, the actual capacity of that shop. Can they actually even fit this through doors, in tanks full of primer, and all of these other things? There's shipping limitations. Maybe I can build this, but can I actually get it on a truck? Can I actually take it down the road, legally? And then finally, maybe I can do all that. I built it. I put primer on it. I got it out the door. I got it on the truck. I'm headed to the job site, and I get into a town, and I literally can't turn a corner because this joist is so big. So many things to consider here when you're looking at joists. In general, the common shipping limit is 8.5 feet wide or 13.5 feet tall, including the trailer deck. So if you're anything over that, it's not that it's not possible, there's just permits required, and that can take time, it can have cost, certainly something to consider. You can probably go up to 16 feet wide or even 16 feet tall with a permit. So shipping limit is not just for the project location, but it's through every state you have to travel. So the job site may not be in the same state where the joist is being fabricated. You need to consider that and work that out with the joist manufacturer, and can even consider that early on when you're designing a building. So one of the things we'll often do in this case, we have a large double pitch joist, and we cannot build it in one piece, or we can't ship it in one piece. One of the things we'll do is we'll actually break the joist into two halves, a top half and a bottom half. Many people refer to this as a piggyback joist. So the joist is actually broken into two pieces. Each half is erected with its own bridging. So it's actually like you're putting two separate joists up. The bottom half is erected with its own bridging, and then you set the top half with their own set of bridging. In the end, the architectural look that you want, a very deep, large gable joist, is what you get from the exterior of the building. So here's a picture of some examples of what that looks like. Kind of hard to see here, so we'll turn on the end a little bit, and I have it highlighted. You can see that, from the exterior, this just looks like a large triangle, a large gable joist, but it actually was built as two separate pieces, erected bottom halves and top halves. So we can work with the design team to come up with a solution for these very large, special double pitch joists. Here's another example. Here's a large bottom half of a horizontally spliced gable joist with square ends. And you can see here they actually haven't even put any of the tops on. They're actually working on erecting the bottom half joist with their own bridging, but you can see because of the end wall there, the block wall there, eventually the double pitch joist is going to be set on top of there, and it's going to match the slope of that end wall in the building. So another thing you can look at is things get very, very large. For instance, it's very deep and it's very long. A final thing we can consider is we can do the piggyback joist, we can do the top and bottom half, but we can actually look at breaking the bottom half into two halves. So actually bottom half one, bottom half two, and we'll put a field bolted splice in that piece. So we actually break the joist into three pieces just so we can get it on, build it, just so we can get it on the truck and get it sent to the job site. Maybe there's specific access requirements at the job site. So we're gonna work with our customers, work with the design team to find solutions here. And again, I'll just reiterate, the earlier on in a project you can discuss these things, the better. So if you have these questions, you're looking at your design, go ahead and give your joist manufacturer a call and start talking about these things as early as possible. And we'll work with you to come up with the best solution possible.
Thank you, Ben, and thank you for everybody in the audience. Appreciate you taking the time to join us today. We're going to continue this conversation about specialty joist profiles. So Ben has been discussing single pitch joist and double pitch joist. And if one of those particular profiles was used throughout an area on a structure, it would provide a very cost-effective solution because it would take advantage of the savings of using a repetitive joist mark. He had some pictures and you saw that all those joists through the entire bay were all the same type. And so there is some economy of using a repetitive mark. So I'm going to continue discussing double pitch joist, but also some other special joist profiles that can be very effective for special conditions. And here we have an image of one of those conditions that's very common. It's a hipped roof. So joist can be used for this type of a roof profile. And it's real common in schools, particularly over gymnasiums and auditoriums, spaces that need a large clear span. And the architectural requirements specify this type of hipped profile above. And here's a picture of an example of that. Here is a high school. It's got double pitch joist that are used in the main portion of the roof. And then at each end where we have this hipped area, there's a different joist profile that's utilized to create that constant eave height around the perimeter. And so this slope rate on this roof is a 4 to 12 slope. So using joist in a hipped roof can be an economical option. And the first type of a layout that we're going to look at uses a combination of the double pitch joist like Ben has been discussing previously, but we're going to add one of these other profile types, and we call this a triple pitched joist. So here's an image of a hipped roof. You can see the profile of the double pitch joist that's used in the middle portion of the roof. And then as it transitions to that hipped area, we start using the triple pitch. And each of those triple pitched joists will have a different profile because the joist slopes up at whatever the specified roof slope slopes up to that hip ridge. It's then flat across the middle area and slopes back down. And as those joists progress to the edge of the building, that profile of those joists change. And overall, it creates a hipped profile for the overall roof structure. And here's an example of a triple pitched joist, which would be the first one erected for a hipped roof. So the slope on the roof is seen at each end of the joist, and that's just the slope rate of that roof. The next joist that would be erected in this roof, it would have a shorter flat section, as those hip ridges move towards the center of the joist span, and eventually they meet and it becomes a double pitch joist. And then the double pitch joist continue through the rest of the building until it gets to the other hipped section at the opposite end of the building. You can look at the ends of this. This is actually a bottom chord bearing joist. It's got square ends with a small top chord extension to provide an overhang. So that combination of using the double pitch and triple pitch joist is especially useful for low slope areas. Say if there's a minimum slope requirement needed for drainage, then that type of a roof layout is especially effective. Now there's also the option of creating these small roof slopes simply by building up the insulation over a standard joist. And we do see this specified on projects. It can be effective if it's in an isolated area where we're using a single special profile joist isn't practical. But another option is to create overbuilding on top of that standard joist or even special profile joist. I'm going to flip back to this sample I showed earlier and point out the entrance area for this building to show an example where overbuilding can be utilized. So there could be double pitched joists for the primary roof area spanning the full width of the building, and then some type of overbuild to create the roof line in the entrance area. So this would just be one option of how to frame a roof line like this. And there's a lot of options for how this can be accomplished. So contact an SGI member joist company if you're looking at options, and we can help talk through different layouts, talk through the pros and cons, and make sure that we address all the needs of the project and find the most economical solution for framing a roof that has a lot of special requirements like this. So the other option for joist in a hipped roof is to provide framing along the hip ridges, and that allows the framing at the hipped end to be rotated 90 degrees. So in this image, we have a hip girder or a beam at each corner framing into a supporting joist. And in this layout, we're using a triple pitched joist to support those hip girders. Now, the reason it's done like this is if both of those hip girders or both of those hip beams were coming into the double pitch where the hip ridges and the primary ridge all come together at one point, it just complicates the framing because it's all coming in at one location. So moving those connections off one joist space just simplifies that framing coming in together and simplifies those connections. One of the advantages of doing this type of a hip roof layout is that there are joists that can provide overhang around the entire perimeter. In that double and triple pitched joist layout, all of the joists are parallel, so there needs to be some different details to provide overhang on the short end at the hip end of the building. So there's one advantage of doing this type of a layout where the hip girders form those hip ridges. And those hip support beams can be a joist or a beam. The beam is typically only if it's a shorter span. If you start getting into longer spans, then you would want to use a hip girder at those locations. And those top chord extensions create those overhangs. One way to support the hip girder is to use a plate connection. Now there's a lot of variations that we've seen on drawings and that we've supplied as a joist manufacturer. So if you're looking at something like this, it's one of those things like Ben has talked about in other situations, is to contact the joist manufacturer earlier in the project to work out these details. Another detail to take note of in this slide is where a triple pitch joist is used, the top chord of the joist is not in the same plane as the roof deck. And so there's this bent plate for deck bearing that's noted in this section. And it's important that that be specified in the contract documents, that needs to be field added to provide the bearing for the deck at that location. So back to the hip girder support. I mentioned that it is an option to use a plate to make that type of a connection, but a better detail is to actually provide a seat at the high end of that hip girder so that it can bear on the top chord of the triple pitched joist. And that makes it cleaner simply because we're now not trying to incorporate special connections within the joist and coordinate those tolerances, but this is a conventional bearing condition of a girder seat being supported on a supporting girder, or in this case, a triple pitched joist. Now, one of the things to remember in this type of an application is that there are a lot of layers of framing. So remember back to those slope seat charts that Ben was discussing earlier, where the high end of that joist requires a greater seat depth. And each of those seat depths stack throughout this structure. And I call attention to that just to make sure that the minimum joist depths are maintained and that the spans can be achieved. So if you think about it, the joist at the hip area of the roof, those are sloped. They have a deep seat at the high end that bears on the hip girder. The hip girder that we see in this picture, it requires a deeper seat for the slope condition that bears on the triple pitched joist. And so just want to call attention to that to make sure that the bearing elevations and the headroom height are coordinated so that we have enough room to get everything to work. So moving on now, in the beginning we talked about pitched chords. Ben made a comment about curved chords, and these are the types of special profiles that those two conditions can create. So a gable joist, and that's what we've been talking about primarily. These are these deep double pitched joists that create these architectural appearances. It's not just for drainage. I mean, it's actually part of the profile of the roof. A bowstring is where we start getting into the curved chord or a radius top chord. And then a scissor and an arch is where the bottom chord is also shaped. It is either pitched or curved to create these other special profiles. So gable joist, this is what we've been discussing primarily as double pitched joist. Again, this is shown here as underslung. It's also an option to make it square-ended with the bottom chord of the joist bearing on the support. We've seen some examples of that. And this would be a curved chord equivalent. This is a bowstring joist. And it has the same options. Again, we're showing it here as underslung, but in a bowstring application, it is also acceptable to make it bottom chord bearing or a square end if that's what the building requirements require. And here's an example of a bowstring joist. You can see the straight, flat bottom chord at the far end of the building, so you can see where that profile is. And if you look at the ends of the joist, these are underslung with that bottom chord below the bearing elevation. Bowstring joists have the same designation depth criteria as double pitched joist. So the depth is measured at the ridge or the deepest part of the joist. A comment about these bowstrings joist is that a flat bottom chord, or I should say a level bottom chord, may not be the most economical profile. So looking at the example at the bottom of this page, if a level bottom chord is required for architectural reasons, it is certainly available. But if it's okay for that bottom chord to slope, it avoids excessively deep portions of the joist, and a better, more economical design is available. In that case, that most economical profile would have the maximum depth at the midspan of the joist. So that might prompt the question of, okay, so where's the ridge? Is it the ridge in the elevation here, or is it the ridge of the joist because the bottom chord is sloping? And the most straightforward answer I can provide is that if there's any uncertainty about how the designation depth should be specified, simply show the overall joist profile on the contract documents. Many manufacturers can provide more than 2 pitched chords. The most common is triple pitched. We've discussed these both in terms of hip roofs, and we've also talked about them being a part of a piggyback joist, those deep gable joists that we break into 2 parts as a manufacturer to accommodate manufacturing and shipping and job site access. Again, contact an SGI member company to discuss these options. The earlier, the better, and we can look at what the requirements are for your project. So these triple pitch joists have a number of different applications. To define the profile of the joist, the ridge locations are required. And actually in practice, as long as the end conditions are well defined on the contract documents, including the seat depth and the elevation of both the bottom chord and the support, the joist manufacturer can determine the required geometry for each of these joists. So it is acceptable to specify joists, say for a hip roof application, and note that the joist manufacturer shall finalize the individual joist profiles to achieve the overall roof shape. And that's because each of these will be different, and it's not required that the specifier dimension all of these, because based on the seat depths and the bearing locations and all the details, the joist manufacturer will dial those in and finalize those to get the required bottom of deck required for that roof profile. Again, look at the shallowest joist to ensure that those minimum joist depths are maintained. And here's another triple pitched joist being flown into a structure. This one looks like it's square-ended with a top chord extension for an overhang condition. Now another variation of the gable joist is a scissor joist. Here, the bottom chord is also pitched. Typically, the top and bottom chords slope at the same rate, such that the joist depth from chord to chord is constant across the span of the joist. In this case, the designation depth is the distance between the top and the bottom chord. And this would be the curved equivalent, an arched joist. Here, the top and bottom chords are both curved. And again, it's common that the radius are set up such that the top chord radius and the bottom chord radius have the same working point, so that the joist depth from chord to chord is constant, and that would define the depth of that joist. And a variation of the scissor joist is a compound scissor joist. So it is not required for the joist to be constant depth, and it's not uncommon to have 2 different slope rates. Or in the case of an arch joist, it's okay to have the top and bottom chord at a different radius if the job has those requirements. We have that flexibility to incorporate those kinds of details into the joist profile. This is another case where an arch or scissor may be required, but a more economical profile is available by making some adjustments. So imagine a gable joist situation, but some extra headroom is necessary. By making it a compound scissor joist, we can add some extra headroom, but not necessarily just make the joist constant depth across the whole span. So if we had a little extra depth at the midspan, that might allow us to be more economical with the overall joist member sizing. And this is another great example where we're contacting an SGI member company to discuss options will allow you to optimize the joist design to meet the requirements for headroom, for appearance, for the joist slopes, but also get the most cost-effective solution for the job. Gable joists are the most economical. The top chord ridge is created during the manufacturing process. Joists with curved chords require that the material be rolled to that radius. So there's just more handling of the material during the manufacturing process. And then when you think about scissor and arch joist, you're doubling the requirements for this special handling, whether it's the pitched chord or the curved chord. It's just another extra step. And I mentioned this to kind of provide a relative cost, but it's not easy to provide a hard cost comparison between all these options because there are so many other variables that affect the pricing. How big the project is, how much repetition there is there additional connection or other coordination required? So when you're looking at one of these jobs and you're looking at options, contact an SGI member company early in the process, and we'd be happy to talk through those options and what the impact of those different things if you're looking at these different types of layouts. Now, when you're using scissor or arch joist, there is a special consideration, and that's that the joist of these types of profile may create a horizontal reaction on the structure, and it's simply that tendency of that joist to spread under load. There's that thrust force. Now, to remove that, a slip connection should be used at one end. So we would still have one end connected conventionally with a standard welded or bolted bolted connection. But at the other end, it would be a roller type connection or with a slip plate. So either a Teflon pad or neoprene or something to accommodate the movement of that end of the scissor or arch joist so that the horizontal thrust reaction isn't applied to the structure. And then there would also be the coordination of the long slots to accommodate that movement. And that would be one of those details to work out with the joist manufacturer during the design of the project. Note that the diaphragm forces collected in the joist top chord would be transferred through that pinned end. Since you've got the slip connection at the other end, it would be the pinned connected end that would resist or accumulate those diaphragm forces. Some other things to talk about when we're talking about special profile joist. I've pointed out some top chord extensions and cantilevers in some of the pictures. We have a underslung double pitched joist here, and a standard top chord extension can be used. Earlier, there was an example when we were looking at the depth charts required for the seats, and we said, or Ben made the comment, the low end is not a concern. When there's a top chord extension, there is the requirement in that it typically requires slightly greater depth just because we have a slope seat assembly that goes under the extension. So the seat depth would increase from a default 5 inches to 5.5 if we had a top chord extension condition. And the other one to pay attention is clearance at the outside edge of the support. Looking in this low end with top chord extensions detail, you can imagine if this support is much wider, it would foul out that top chord extension. So that seat depth will ensure that there's clearance between the top chord extension and the support. Just another detail to pay attention to when laying these out. Another condition is for a bottom chord bearing gable. and it is acceptable to have a full depth cantilever. These are nice if you start getting over 6 foot long extensions. 6 foot's a good rule of thumb for a maximum top chord extension, that previous detail I showed. We can go longer than that, but you want to kind of start coordinating to make sure we have enough seat depth and enough extension depth to develop whatever loading requirement is. But these type of full depth extensions, we've done these even beyond 10 feet, and it's with the web system, there's no concerns about developing that capacity in this type of a configuration. Another consideration talking about special profile joist, typically fabricated with no camber. Special profile joists often have very large depths, and that creates very stiff joists such that there's often much less deflection of one of these very deep profile joists compared to a standard joist. So thinking about a 70-foot joist, default SGI camber would be 2 inches. And if the top chord were sloping at 3 to 12 or 4 to 12, a no camber requirement is probably a good decision. That camber isn't required to maintain the slope or the drainage for that roof. So no camber is very common for these special profiles. And if not no camber, then possibly a specific non-standard camber. So maybe instead of 2 inches, maybe half the camber, or maybe a requirement to camber for a specified dead load. So these are just details to consider when specifying these products on a project where those contract documents need to reflect this requirement. And then looking at some special profile joist. Here's an arch joist, top and bottom chord with curved. It's bottom chord bearing. We have a cantilever condition at the eave. The top chord actually extends beyond the support, and the last web member extends out to support it. Here's a bay of some scissor joists. These are underslung. And even with the underslung end condition, the slope rate is large enough that bolted erection bridging is required. Ben made a comment about this, but that bolted bridging is installed as the joists are set, so that they're bolted in before the hoisting cables are released, since the joist would be unstable under its self-weight if it was just set there and released without any bridging installed. So this type of a configuration would require some bolted erection bridging. And here's some joists with a little bit of everything. So you can see we've got a double pitch top chord. It's underslung. The bottom chord is radius. There is a field splice. It's kind of hard to see in this picture. It's fairly small, but these were shipped to the job site in 2 pieces with a bolted field splice. So they were bolted together and then erected in place. And then there's even a little extra turn at the very end where the bottom chord turns level at each end. And this just kind of brings some attention to, we've shown these joists with either underslung ends or square ends. It's acceptable to mix those if the project requirements have different conditions at both ends. That's not a problem to have it bottom chord bearing at one end and underslung at the other. That works. And talking about special profiles, I have seen a job where both the chords were curved, but the bottom chord was what I would call reverse curve. So basically it created like a football shape. So we have a lot of flexibility in how we configure these special profile joists. So some best practices. Optimize the joist spacing. In the example Ben ran through, he used a 10-foot joist spacing, and for a lot of configurations, that makes sense. If we think about a joist with a reasonable slope rate, 3.5 to 12, even at a 60-foot span, the depth at the ridge is 120 inches. So this thing is 10 feet deep. And often the joist manufacturer will use some minimum member sizes just to facilitate handling and shipping so it doesn't get damaged. So a lot of times the design loads aren't the controlling factor for the member sizing, which is to say a lot of times there's extra capacity, or that if these joists were spaced wider, they might get nominally heavier, but if you went from 5 feet wide, 5-foot spacing to 10-foot spacing, you're not going to double the weight of the joist. So it's typically more economical to use these types of joists at a much wider spacing with a deeper roof deck to have the optimum joist and deck system. Often have cords controlled by minimum sizes for handling rather than the load requirements. And that's why I'm saying a wider joist spacing is typically the optimal layout. And using a 3-inch roof deck allows that extra capacity to be utilized. It's essential that all the geometric requirements of the joist are on the contract document. So either accurately specifying the designation depths or simply showing a profile of that joist so all the dimensions are called out. And if a standard SGI designation isn't appropriate, using load over load designation. Where additional load requirements exist, provide a complete load diagram. Remember that standard SGI camber may not be ideal for the project application. When you consider the transition between areas with special profile joist in the adjacent areas, maybe it's a beam line. We had a picture where there was a block wall that was the edge condition. And so that transition between the last joist and that adjacent area may require different camber than standard SGI. So either zero camber or a specific requirement should be specified on the contract documents. Specify the means of the bridging termination. If needed, the joist manufacturer can provide termination bridging in the last space between joists if the bridging can't or shouldn't terminate at adjacent framing. Another best practice is that if there's additional structural bracing required, note that on the drawings rather than assuming the joist bridging will serve that purpose. That joist bridging is intended to provide the lateral support to the joist under self-weight during erection, and also for cases where there's stress reversals like uplift or end moment. So that joist bridging is there to provide the bracing for the joist. If other structural bracing is required, specify that as a separate item. And then the boundary conditions, the supports where we have these special profiles like arches and scissors, where there's going to be a horizontal thrust to specify how that support detail is assumed to be handled. We have seen projects where it is a fixed connection at both ends, and we simply provide that developed horizontal thrust so the engineer can incorporate that in their designs. Again, one of those coordination things that contacting the SGI member early allows all those details to be worked out on the front end.